Hi, my name is Romeo Bruni, and today we're going to discuss one of my favorite subjects, and that's supermassive black holes. Very important to distinguish supermassive black holes from ordinary black holes. They are not the same creature. There's two huge differences between them. The first is sheer number. For example, in the Milky Way, there are 100 million black holes, but only one supermassive black hole. And in fact, almost all galaxies have one and only one supermassive black hole. There have been a few galaxies that they presumed maybe don't have one. There are some galaxies that may in fact have two. The ones that don't have one probably lost them in a merger. The ones that have two probably gained them in a merger. So in terms of formation, they probably, each galaxy when it's formed develops one supermassive black hole. The other huge difference between supermassive black holes and ordinary black holes is their sheer size, their mass. Ordinary black holes, for example, in the Milky Way or any other galaxy, will have anywhere from 10 to 100 solar masses. But supermassive black holes have masses hundreds of thousands of times bigger. Supermassive black holes have galaxy masses anywhere from millions, 10 to the 6th, to 10 to the 9th solar masses. So we're talking either millions to billions of solar masses. The Milky Way, Sagittarius A star, is our black hole. It has a weight of a mass of 4 million solar masses. Andromeda, our nearest nearby spiral galaxy, has a supermassive black hole, much bigger than Sagittarius A star, but still relatively underweight. It's only 100 million solar masses. The biggest supermassive black holes in the universe are measured in billions of solar masses. For example, there's one supermassive black hole, Ton 618, that weighs 66 billion, that's with a B, solar masses. So because there's only one in every galaxy, and because they're so much heavier than other black holes, they're a completely different creature, so don't even think of them as being black holes. Because they're so big, their formation is still a bit of a puzzle. It doesn't seem possible that they could have gone through the normal phase of a star getting super large, running out of fuel, and collapsing into a supernova, which is how black holes are normally made. A black hole, supermassive black holes at the center of Saturn galaxies are not made that way. It is not exactly clear how they are made. There's various theories. I think the most likely thing that it is condensing cold dark matter clouds. When dark matter is compressed, it doesn't heat up. So cold dark matter cloud compressing and heating up will achieve high densities without getting hot enough to ignite nuclear fusion. So you can have a direct collapse into a supermassive black hole without having to go through a star phase. So size is different, numbers are different, formation is different, structure. When it comes to structure, what develops around a black hole is not that supermassive black hole is not that much different than what would develop around any black hole. And that is because black holes are spinning and because things in the universe tend to be spinning and have angular momentum. Stuff spinning or being attracted towards a black hole is going to form an accretion disk. An accretion disk is a flattened disk that forms along the equator of rotation of a very heavy object, for example, like a black hole. Of course, an exception of an accretion disk not around a central heavy object is a spiral galaxy, where it's the dark matter itself providing the gravity well that accretes the whole spiral galaxy. But around black holes and around certainly supermassive black holes, you're going to have an accretion disk circulating around the black hole. Now, the accretion disk is matter, and this matter, as it circulates, heats up, such that on the inside it's going to start to get very hot. On the outside, it's not so hot, and giving off infrared light. As it gets hotter and hotter as you approach the center and towards the inside, it starts starts to give off even higher energy, right, up to X-rays. So the accretion disk itself is going to give off a lot of light. It's going to be a black body spectrum because there's going to be light of every wavelength given off because all the different temperatures are represented as the accretion disk gets hotter and hotter as you approach relativistic speeds. That's near the speed of light, near the center. So the accretion disk itself is going to be very bright whenever material is being fed into the black hole. When no material is being fed into a black hole, it's not going to be all that bright because it's dependent on material being fed into it. It's much more efficient in turning that material into energy because in a normal nuclear fusion, hydrogen to helium, you get only 0.7% of the mass converted into pure energy. With accretion disk, you can get up to 10% of the mass converted into energy. So accretion disks are powerful light sources. In addition to the accretion disk, what you have are jets. And jets are plasma. The whole black hole is spinning, and the accretion disk is ionized and spinning, and this turns the whole black hole into a huge particle accelerator, like a huge magnet, and that shoots jets out at the poles. And the jets will be shooting plasma, electrons, photons, ions, at relativistic speeds. That means speeds approaching the speed of light, up at two jets perpendicular to the accretion disk plane. These jets, because they're moving particles at such high speeds, release radiation. It's one of the two ways in which radiation can be released, really, other than jumping from electron orbit to electron orbit. Another way it can be released is something called synchrotron radiation. And synchrotron radiation is when charged particles accelerated perpendicular to their flight path give off radiation. And so the jets themselves will give off light. This light depends in the radio wavelength, but it can be in other wavelengths too. But predominantly, because it's in the radio wavelength, these are called radio galaxies when we see them. So let's check off a few things. We've discussed the number, the size, the formation, the structure. Active galactic nuclei, AGNs, are any supermassive black holes at the center of galaxies that are shedding a lot of electromagnetic radiation, whether it be bright light, in which case it's called a quasar, because there's a lot of bright light being emitted. If it's a lot of radio light being emitted, then it's called a radio galaxy. If the jets happen to be oriented so that they're coming directly towards us, it creates an unusual empowering of these jets so that they become what we call blazars, where the speed of the particles moving towards us actually seem to be moving at faster than the speed of light. Of course, they're not. This is called supraluminal velocities. So those are blazars. Seyfert galaxies are just quasars that aren't as bright as the most luminous quasars. So when they're very luminous, they're called quasars. When they're not so bright, they're called Seyfert galaxies. When, for some reason, we're not seeing that much light from the accretion disk, it's either obscured or it's at the wrong angle from us. In which case we see predominantly the light coming from radio, from the jets, then we'll see more radio wavelengths than anything else. Then it's a radio galaxy. But they're all forms of supermassive black holes, just depending on the angle and how much stuff they're eating at the time, and which determines how bright they're going to be. So all quasars are obviously supermassive black holes, but not all supermassive black holes are quasars, because some of them are not eating a lot of material. For example, Sagittarius A star at the center of our galaxy is not eating a lot of material, so is quiescent and will not be very bright. A very beautiful diagram I like to show is this one. And this is M87 Galaxy. M87 Galaxy is a huge elliptical galaxy that's 60 million light years away from us. And here we see it with Hubble in visual light. And you can see it's a huge elliptical galaxy providing this glow. And then from at the very center, we see the quasar emanating its light. And then we see one of the jets. So we have the galaxy, the quasar at the center, and the jet. You can see how enormous the jet is. And this same galaxy now in radio wavelengths, we can look at the same zoom here in radio wavelengths, and you see the amount of radio waves coming also from the accretion disk, but the amount of radio waves coming off the jet is enormous. And then, of course, in radio waves, if we zoom in, you see this famous picture of M87. You're actually seeing the accretion disk around the dark area at the center, which is the black hole, and you see the accretion disk. You can see, obviously, a quasar. Now we're looking at this same structure through all the various wavelengths. You see a quasar is also giving off light in all the wave strengths. Up here, it's giving off light in gamma waves, sorry, X-rays and gamma waves, and in fact, even cosmic rays are being given off. So quasars and galaxies obviously produce a lot of light. When you examine them, you can figure out where it's coming from. And a lot of it is going to be coming from supermassive black holes. My name is Romeo Bruni. Hope you enjoyed this chat.